now recording. You can start.
Okay, I would like to thank everyone for being here. So this is second part of this lecture series on hypergeometric functions, character sums, and applications. So my colleague Fantine and I are writing the notes together. We make the first part, the primitive part, available. We are still working on the remaining part, but I will actually send the slides over today. Right? So according to the plan on myself, today I'm going to talk about the finite field aspects. And so a few goals I set up for today's lecture will be, I'm going to introduce hypergeometric functions over finite field in a way which is parallel to the classical setting. And then with which we can attain many character sum identities. And then hopefully we're going to use that later. And the second part, I'm going to relate hypergeometric character sums to point counts on algebraic varieties. So let me briefly go over, because this is going to be parallel to the classical setting. So this is from yesterday. The key properties of the gamma function. The gamma function is defined. Given x, there are two parts. One part will be, this part is multiplicative in t, and this part is additive in t over here, and it satisfies the refraction formula and multiplication formula. So this is the double angle formula, but there are other multiplication formulas. And for the finite field, so let me first set up the notation. Here for this lecture, P will be an odd prime. So I'm excluding 2 for this lecture over here. FQ will be a finite field of size Q, which is a power of P. And if you remove 0, invertible elements in this finite field is forming a multiplicative group. The order will be Q minus 1. So then we can actually talk about homomorphisms from the invertible elements to fields like C or CP later. Then they are forming a multiplicative group structure. The omega, or here, will be a generator. And also for the convenience, epsilon here will be the trivial character. And because of the assumption on the characteristic being odd, there is a unique quadratic character, which is called the phi over here. And in this current setting, all the chi, which are multiplicative characters, have finite order. So chi bar is going to be the inverse, right? And the other convention we're going to set will be when we're doing the extension to 0, all multiplicative character at 0 will take value 0, including the trivial character. So this is sometimes the other textbook use 1 for the trivial character, but for here, for our convenience, we would like to make everything multiplicative. So the value at the trivial character will be 0 as well. And the other thing we're going to fix will be the chase, the additive character, which is the chase, the value from the finite field, the chase from the finite field back to the prime field P, and then you let zeta P, which is a fixed primitive piece root of unity. So you fix zeta P, then you raise to the chase of the element X, which is an additive character for the finite field. So that will be actually fixed. And now there are also other 2 more notations will make our life a little bit easier. One is called the delta function. If delta applying to a character, that means this value will be 1 if you meet the trivial character. Otherwise, it's going to be 0. And the other delta function will be applying to elements. And the value will be 1 if you see 0. Otherwise, you will see 1. If you see 0, you see 1. If you see something non-zero, the value will be 0. Right? And then because of characters have a lot of orthogonal properties, one of that will be if you apply the additive character And then you actually summing over all elements in the finite field. So you are summing over a bunch of root unities. So what you will get will be 0. So the other thing will be the orthogonality for multiplicative characters. If you take the so-called inner product of two of those elements, summing over all the invertible elements, and then you apply chi to x, and then the inverse of the second character to x as well, summing over all the invertible elements, with normalized by the size of the invertible elements, what you will get will be the delta function for characters. So this is convenient when we get to finite Fourier analysis. So basically, if we have a function from the finite field to C, you can write as the following, because a basis from all such functions from FQ to C can be written in terms of the delta function, as well as all the multiplicative characters. So you can write down the value at F0, you put the delta function, and then for the coefficient in front of the multiplicative characters, you compute the inner product of your function with the corresponding multiplicative character. So you get the formula for expressing this hand sign over here, f of x, in terms of delta function and multiplicative characters. Right? So now we get to the function, the definition for Gauss sum. If you have a given multiplicative element, let me put over here. So if you have a multiplicative character, which is written down as A over here, we can define its Gauss sum by very much definition similar to gamma function. So you take this multiplicative character and then couple with the additive character. Then you sum over everything in the invertible elements. And then what you will get is so-called the Gauss sum, which is actually a very kind of fundamental character sum that you will deal with in number theory. And we all starting with the property of Gauss sum, and we know that when we apply Gauss sum and then times Gauss sum and its inverse, which is down here, let me see, you get to basically it's a plus minus 1 times the size of the finite field. And of course, the story will be different if you get to the true root character. So what you will see, because of the true root character, if you compute the corresponding Gauss sum, it's almost adding up everything inside the additive character except 0. So the whole thing becomes minus 1. It also tells you that there is a discrepancy when you take the Gauss sum and Gauss sum inverse, and then there is a delta term coming in. Actually, for as far as I can see in character sum calculation, the delta term is actually one of the very tricky things to deal with. So, and because of these properties, when you look at non-trivial multiplicative character, the absolute value for the Gauss sum will be square root of q, which is very homogeneous for all the non-trivial characters. And now I'm going to mention about one of the Hasse-Davenport relation, which is the multiplication formula for Gauss sums. So it's very parallel to the multiplication formula for gamma function. So what it says over here, it's if you have any additive character, and what you can do is you can multiply the additive character with all the chi over here. So this is actually all the multiplicative character whose all the divisors of this fixed number m, and also the assumption will be the size of the finite field is 1 modulo m. So you do have m of those multiplicative characters. So if you're going to kind of rotate your psi with chi raised to, all different choices of chi, what you will get will be this side that you have chosen raised to the power, so it's multiplication. So on this hand side, if you write as a, as this psi over here, then the chi will be different power of m. So you take a product, all right, in the complex case. This is the analog. And then this is going to be the analog of m times a. And plus the gamma value applying to those corresponding I over m over here. And plus there is a power. There is a very explicit power in the middle, all right? So which is the Hasse-Davenport relation. And it turns out that the Yamamoto proof, which is a conjecture by Hasse, that if you look at the case, if m is any even integer and p satisfying the property that is 1 modulo m, which is applying, then more or less the refraction formula we mentioned in the previous page and the multiplication formulas are by the divisors of this guy are the only two types of relations among Gauss sums for all the multiplicative characters whose order dividing this m over here. When they are considered, when Gauss sums are considered, generating as ideals in the ring of algebraic integers, which is actually a pretty nice result because in a complex case, people do want to know, for instance, among all the gamma functions with, say, base over here to be 5, how many different relations between gamma 1, 5, gamma 2, 5, gamma 3, 5, etc. It's actually unknown for the complex case whether only two types of relation among those gamma values, namely the refraction formula and the multiplication formula. And very similar to the complex case, we can define Gauss sum. So Gauss sum is the analog for the beta function. So given a pair of multiplicative characters a and b, we can put them together in terms of some kind of convolution over here. So you apply x to a, 1 minus x to b, and you're summing over all values in the finite field. And the relation to Gauss sum is when you look at a and b, if you put that into the Jacobi sum, the Jacobi sum turns out to be Gauss sum of a, Gauss sum of b, and then over Gauss sum of a times b. Right. But the situation will be slightly more complicated if the product is going to be a trivial character. So there is a delta term coming in. So this formula also tells us that when a, b, and a times b are not trivial, none of them is a trivial character, then the absolute value again is going to be square root of the size of the finite field. Right. And now we're going to use the notation that choose character B from character A means it's going to be Jacobi sum of A, B bar with a psi in the front, right? So this will be making the formula looking a little bit more parallel to the classical case. So now we're going to do the finite Fourier analysis to one of the basic function, which is given a multiplicative character. We look at its inverse, and then we evaluate the function, this a bar applying to 1 minus x. And by the formula providing before, when x is 0, you get a or 1, right, which is 1. So the delta term is delta x. Then you take the kind of the inner product. So this is the normalizing factor for the inner product of your character a bar with chi bar, right? Then what you will get will be basically a Jacobi sum. So this Jacobi sum kind of equivalent. There is a relation between this Jacobi sum and the Jacobi sum I'm actually telling you, a bar and chi bar, all right? And with the sign over here, you can rewrite it in the way which is actually pretty parallel to the classical formula. This is 1 minus x to the minus a over the complex setting. So you can write it down in terms of the rising factorial. And I would like to mention before I go ahead what I call a vertical Hasse-Davenport relation. The vertical Hasse-Davenport relation says if you have FQ and then you consider its degree R field extension, and of course you can take the trace and norm map to go from the extension back to FQ. Now, if you have a multiplicative character from the FQ down here, you have chi, which is in here, then you can lift it up, all right, by first applying the norm map and then compose with the chi if you have an element. So this is a multiplicative character for the bigger field extension. And this induced character is called chi of R. And for the definition of additive character, it's always the same. So now if you compare the Gauss sum for here, which you have G chi down here, and then you have a Gauss sum up here, G chi R. And then the Hasse-Davenport relation says, basically, it's actually more convenient to think about the correct definition of Gauss sum, which was in the older days, they used negative of the current notation. So negative of the Gauss sum of the current notation is the old Gauss sum in the bigger field down here. It's the smaller Gauss sum down to the base field FQ to the R's power. So which I will call it as a vertical Hasse-Davenport relation. And in comparison, the other horizontal one will be you work on the same field, you're doing the multiplication formula. Now I'm going to kind of go over the definition, which is actually in my long paper joined with Jenny Fuseli, Ravi Ramakrishna, Fountain 2, and Holly Swisher Fountain 2. Then we're actually kind of trying to compare the character sum in the way which is parallel to the classical setting. And then the way we concluded will be, we should actually think about the finite field setting in the light of the period function that I actually defined yesterday. So we're starting with the basic one, which is 1 minus the argument z raised to minus a1, if that's the parameter set to start with, a1 and 1. And then inductively, we can define the period function as iterating integrals. For 2p1, it's written in this way. So in the finite field setting, applying the same idea, what we are going to write down will be given a multiplicative character A, and down here there is the trivial character. This is the starting building block. Lambda here is the variable. Q stands for the size, means which finite field I'm working with. Then the definition will be this function is going to be the inverse of A applying to 1 minus lambda. And inductively, we can define other period function from the previous one by doing again the truncation. I'm going to truncate the first part of the period function, the parameter set, put down over here, and then use an additional variable y, summing over y. So this is actually the analog of the integration, okay, dy. And then in front of it, we're going to put some kind of twisting factors according to the last set of multiplicative characters which are given. So these are parallel to the classical case over here. And when there is no ambiguity, the Q might be dropped. Okay. And according to this inductive definition, the 2p1 function now with 3 multiplicative characters, there will be A, B, and C. in terms of formula, it's going to be the B character applying to X and inverse times C applying to 1 minus X, the inverse of A applying to 1 minus lambda X. From the definition, it's obvious to see that typically, for most of the cases, I cannot arbitrarily change B and A. So this is not going to be true in general. And when myself first came to character sum, this is something I feel like in the classical case, if you look at hypergeometric function, they are symmetric. But if you define character sum in the way which is parallel, it's not. But the difference is very kind of minor. We can do a normalization later, which can remove the inconvenience that I mentioned over here. And you can write down everything in terms of either Jacobi sum or the binomial notation down here very explicitly. And for this case over here, so just briefly look at the values, right? So if I'm doing a naive count for the values, the absolute value, I know that this term over here is square root q. Basically, this one's also square root q. I have more or less q of them summing over all together, dividing by q minus 1. So you can see that basically this count over here, the naive absolute value will be around q. Okay. And later, when we get to Galois representation, we can actually give a smaller bound. Okay. For the case down here, it's actually relating to Hasse's bound. It's 2 square root q down here. Okay, it will be actually a refinement. Right. Now, pretty much motivated by the classical definition, we're going to try to remove the ambiguity that A and B play asymmetric role by the normalization. All right, the normalization factor is actually the same as what's the value for the periodic function when lambda gets value 0, right? Which is the reference point. The normalizing factor is I'm going to make the leading coefficient to be 1. And more or less, this is the motivation, how to do the normalization. It turns out to be a Jacobi sum. And after this normalization, in the case when AB are non-trivial characters and ABC are not the same, that means the sets to be primitive. Then we can kind of swap the role of A and B, they will be the same. All right. If I interchange A and B, it will be basically the same value, which is pretty convenient and parallel to the classical case. All right. So likewise, you can define the normalized period function in very much the same way. It's actually naturally, then you would do the same thing. Just like the classical case, you would do what's on the finite field case, right? And with that said, I want to say that why I want to mention this, I want to mention that at the first place, there is a kind of a parallel setting, then you can try to attain hypergeometric formulas over finite fields in the way which is pretty much parallel. All right. And say last time, yesterday, I briefly mentioned that some of the formulas over the finite field can be defined in terms of either definition or setup, or from comparing coefficients, or from specializing values. And some of this technique then you can actually generalize immediately from the over C setting to the over finite field setting over here. I think today I'm actually skipping a lot of pages, but anyway. So let's continue down here. So yesterday, I do mention one of the Gauss evaluation formula, which is a very nice formula providing a lot of special values as CM points. And the 2p1 function that I defined yesterday, when we evaluate it at 1, we get a explicit gamma function, gamma value here. Sorry, this is a beta value. So it's a beta b and beta c minus b minus a. And this formula is attained by the setup or by the definition of beta function. We can do the same thing for the finite field setting. If we have 3 characters A, B, C, and at 1, again, by definition of Jacobi sum, we get to this formula, Jacobi sum of B and C and A, B bar over here. So this is very much parallel. So the translation here will be little b to capital B, and then C to character C, and the bar here, which means the inverse. So the inverse of B and inverse of A. So everything's kind of in a very parallel manner. Okay. And the other formula I want to go over, because this formula will lead to one of the formula I use a lot, right? It's the Kummer transformation. The Kummer transformation says if you do have 2f1, a, b, c, and x, and then it will be the same as the classical 2f1, c minus a, c minus b, and c here with additional 1 minus x raised to c minus a minus b to the front. So this can be proved in several different ways, including you can use rigidity. All right. Over the finite field setting, and the corresponding formula will look exactly very parallel, that you have ABC on the finite field correspondence. And here, the 2f1 case, you have C minus A, so that translates into C and A bar. And then C minus B translated to C, B bar, and C goes to C. And the 1 minus x, according to our formula, which is 1p0, goes to C, A, B bar, applying to 1 minus lambda. But for this formula down here, there is a delta term. The delta term turns out to play a special role when we get to the Pfaff-Charchus formula, which is attained for the classical case. Will be comparing coefficients that I mentioned yesterday. So if I comparing coefficients for as formal power series, I can doing the coefficient expansion. There are 2 parts. There is a coefficient coming from this part, coefficient coming from this part. I need to put them together. That corresponding coefficient should be the same as this hand side. So that leads to the Pfaff-Charchus formula. All right. In the finite field setting, we can do exactly the same thing over here by comparing coefficients. The major term will be this term down here. It will be actually exactly comparing coefficients when we get to the major term. I mean, the major term on the right-hand side will be this particular term. And plus, because of the remaining delta term, there is a kind of tail, which is additional term over here, kind of funny and interesting, because this is value at 1. I'm going to get to more tomorrow what happens at 1. All right, what happens at 1 is, unlike other cases, it's the degeneracy happens at when the argument is 1. In particular, Pfaff-Charchus formula says when the parameters, when you take A, B, C, you take a product, it's the same as the product of the lower characters. If you multiply the lower characters, it's also A, B, C. So what you will get will be 2 Jacobi sums, but they of absolute value to start with. So this guy will be, in general, square root q times square root q, which is the major term. And this is square root q as the minor term. So there is a discrepancy here about the absolute value. And the other formula I would like to mention will be the Kummer evaluation formula. The Kummer evaluation formula says at -1, which is actually a derivative of Gauss evaluation formula. So it says that at -1, you can actually compute the value by specializing -1 to one side of the Kummer quadratic formula, and then you get to this formulation. I would like to mention that this case now bring another interesting phenomenon. The phenomenon says in the finite field setting, you're doing the same computation, but situation will be kind of different now. The difference lies in, it depends on whether C is going to be a square. And why it matters is in the classical sense, when we write down -1, we are actually getting to C over 2. C over 2, if we think about C correspond to a character, C over 2, somehow it will be a funny kind of phenomenon. It says, I'm going to take a square root of a character. Right? If it's still a character, however, this will mean I do have two choices. That means it will be either D or D times the quadratic character. So if we go directly from kind of the analog for comparing, kind of making rational numbers into characters, then C over 2 will give you actually a priori two choices. And in the case when I cannot take the square root, that means C is not a square, the value here will be 0. If it is a square, then there are two ways I can translate the formula up here. One will be in terms of this very explicit Jacobi sum. And keep in mind that delta, the D over here, the square root do have two choices. So the other choice will be phi of D bar. So we do have two parts. So it tells us that there is something going on for half of the chances, the value will be 0. For the other half of chances, I will get to two values. They have the same absolute value, and then there are actually correspond to different choices of square root of C. Okay. So this is the Kummer evaluation formula. And of course, I showed you a lot of formulas that are very similar. And I want to actually give you now some warnings. Do not take the similarities for granted. All right? It's actually kind of easy to think. Now, what I have talking about over here is basically, I call it a dictionary. John White said that, oh, it's not quite a dictionary, but it's actually pretty analogous in the sense that the dictionary I mentioned will be now you have a way, which is I call it calculus way of translating classical formulas. The way to do it is if you have a rational number A, I can correspond to a character. So the feature will be this A will have a denominator, all right? So there might be an integer you multiply, you will get to an integer. Then A, I will take it as a character, raising to the same power, becoming the trivial character, all right? And then gamma A, I will translate into Gauss sum of A. And if it's x to the A, that it's A to the x, etc. So this is actually a very parallel way. Then you can do a lot of kind of calculation very parallelly. And however, the warning I'm giving you will be, do not take the similarities for granted, right? So for example, in this page, I'm showing you another, what's called the Kummer relation. The Kummer relation, there are 24 of them. Basically, they're relating to the linear transformation on CP1, which is fixing kind of permuting 0, 1, and infinity. Of course, one way to do that is sending Z to 1 over Z. The other way doing it will be Z to 1 minus Z, etc. So correspond to this linear fractional transformation, permuting these three singularities. This Kummer relation says if you start with 2f1, a, b, c, and z, if you write as a new variable, which is analytic continuation from 0 to 1, what you will get to will be this particular 2f1 with a gamma factor, gamma of c minus a minus b, gamma c minus a times gamma c minus b. And there is another part over here. However, such kind of formula will be simplified greatly over finite fields. Over finite fields, what you will see is this is more or less correspond to the left-hand side. It's correlating to the first part here on the right-hand side with only a character in between. So it tells you that these two, if you go to the finite field, they are more or less correlated up to a character. So it's kind of inconvenience if you look at that correspondence, because yesterday I spent some time to talk about the inverse of the lambda function. It's given by this Schwarz method, which is also called mirror method in physics. So if we recall what that is I have two solutions for the case when alpha to be 1/2, beta to be 1/1. And there are two solutions. One solution, which is holomorphic, near 0, will be this one down here. And there is another one with log solution, will be the one up here. And they are not scalar multiple. And the ratio will give us an interesting Schwarz map corresponding to the inverse of the lambda function. And if I look at the finite field setting, if I'm doing kind of the analogous kind of consideration, basically we will get nothing out of this picture. All right. So the outcome is very disappointing if I use that to consider the finite field analog. All right. So that tells me that if I consider things in this perspective, the finite field setting, I should interpret things differently. All right. So another example will be this one down here. This is an algebraic hypergeometric function. If I look at 2f1, a minus 1/2 2a, and it's going to be this algebraic function. Right? Of course, if we look at the finite field analog, we will say that if I'm practicing my skills of writing down what that is over finite field, I write down this is a character a, this is a character a times a quadratic character, this is a squared, this is z, all right? So far, so good. Then the right-hand side, I will say that, hey, this is going to be a, negative means bar, 2 means square, and then 1 plus square root 1 minus z over 2, all right? Then we'll say that, hey, how about they are the same, all right? You might think about, naturally, I might translate this formula in this way. And the answer is no, it's actually not that, all right? The answer will be you need to put two kind of conjugates together, all right? If you have a square root, if you're radical, you do not have actually a priori a way to distinguish which branch you are using. So you need to put both of them together. And again, very much like the Kummer evaluation formula, when you get to the case when 1 minus z is not a square, the value will be 0. Otherwise, you cannot distinguish which one is which. So what I want to say is, this is actually a lot of fun if you're trying to translate the classical formula using the dictionary way I'm telling you.
In the classical formula, though, there is some kind of determination of the square root. It's not ambiguous.
Yes, I mean, the way we actually determine, it's actually you can, depending on which point you're considering, all right? You can actually fix a point that you like to, because there is some holomorphic kind of way of consideration, right? So I'm actually considering that formula. It depends on which point we are doing the expansion. Again, there is ambiguity which way, which of them you are using. And the main point, I mean, we should be very careful when we claim such a formula, which is a formula in the literature. When we're doing the finite field analog, we need to be be careful that the main thing I'm trying to warn you will be, while the classical formula very often represent a single function or single solution to the differential equation. The finite field analog, on the other hand, by nature, is going to be an average. So it's a trace function. So by nature, they are different. And that's also why when you get to the Schwarz map, it's average over average. So you do not get much out of such a ratio, right? Any other comments? All right, so before we taking a break, I would like to mention there are two views of hypergeometric sums. All right, so I will actually put on this picture over here. The two view I'm actually referring to will be, there is a horizontal view, which this I mean, for example, if you're doing the calculus style of kind of correspondence, 1/2, which is a kind of a rational number, corresponds to, without any ambiguity, the quadratic character for any finite field of odd characteristic. There is no ambiguity. And then the kind of the setup I'm giving you will actually translate or write down the formula for this 2p1 function as this sum over here. Then you can vary over finite fields as long as it's in this current setting is different from 2. So you can go from f3, f5, etc. So it's kind of horizontal variation. So I'm going to talk more about that tomorrow. But I want to also emphasize, because I might easily forget later, there is also a vertical point of view. The vertical point of view is actually you can go down from the field extension back by using the norm map. All right. The vertical point of view, basically, it's relating to the local zeta function. Right? But I do want to mention that. And for a fixed prime number p, so we can vary the characters vertically by using the norm maps. So for instance, if I'm going to compute the zeta function for alpha, beta, and lambda over here, we can assume to be in fp with an additional formal variable t. What we can do is there is a sign over here. The sign is relating to what's the length for the alpha set. It could be plus minus. So without that, what we will get is either a polynomial or reciprocal polynomial. This is going to be correct, the outcome. So you can take the lifting of the average function, which is 2p1 function. Without any ambiguity, you can choose the quadratic characters in the finite field of PR. And then you put the formal variable t to the r to the top and dividing by r. And then you can take the exponential function. All right. Then we want to remind you that because the log function, if you're doing the expansion, is pretty much looking like what I'm telling you down here. All right. Then you have to be careful about the sign over here. And with that definition, if you put the character sum vertically, what you will get will be something that's pretty nice. Let me just give you an example. When we get to the Kummer evaluation, when p is going to be 1/4, so the trace is not going to be 0. And now you can apply the formula to the previous page, and we know by Kummer evaluation, you get to Jacobi sums. They are putting together Gauss sums. Gauss sums have the vertical Hasse-Davenport relation, so you can write it down in terms of Gauss sum of this character and Gauss sum of this character dividing by the product. And they can be lifted up by Hasse-Davenport relation to finite field extensions. And because of the Hasse-Davenport relation, you can write things down in a very explicit way, comparing to the formula for the log 1 minus a t formula. You notice what I'm going to get will be a polynomial, which is degree 2. And the two roots are related by, if one of that is mu p, the other will be p dividing by mu p. And in particular, you can take this mu p to be one of the Jacobi sums, where eta 4 is an, by the assumption over here, there exists over the prime field an order 4, primitive order 4 character. You can use any of those. And phi again is the quadratic character. All right. So that's what I want to say. That's the vertical view of what the viewpoint consider when we look at character sums over finite fields. All right. Any other questions or comments? And with that, I think it's a good place to take a break.